Um, in this section, we're going to talk about conservative forces. So there are two definitions for uh, conservative forces. There are two ways of defining conservative forces. The version one is a force is conservative when the work does on a moving object is independent of the path between the object's final and initial position. So we know how to define the work. So work is force times displacement. If the displacement is F, and if you apply a, this is the, let's say this is the initial position and this is the final position, and if you apply a force, work is equal to force times displacement. Let's assume instead of going from initial position to final position along this straight line, we go like this. We just go like this. So a force is conservative when the work does on a moving object is independent of the path. So if the work we're going to calculate is independent of the path, which means it's only depend on the initial position and final position, then we call this force is conservative. Okay. And the second version of conservative force is when an object moving in a circular orbit, or if the initial position and final position close path, starting and finishing at the same point. It doesn't need to be circular. It can be you start from this position, go up and come back down to the same position, or you go this direction, then turn around and come back to the same position. So initial and final position is same or closed path, then that force we apply to take it around this closed loop or go up and down is conservative. That force is a conservative. So there are two cases. If the work is independent of the path, then we say this applied force is conservative. Or if the object come back to the initial position, then again this force is conservative. So gravitational force, elastic spring force, electric force. So if you have a spring and you can stretch, you can apply a force and then you can stretch the spring, and when you let it go back to the initial position. So this force on this string, we call it elastic spring. And non-conservative forces are air resistance, tensions, normal. So far we talk about conservative forces, and next few slides we will talk about non-conservative force. But in this chapter we mainly work on problems associated with conservative force. Okay, here's another example. A force is conservative, so this is a gravitational force. If you let it goes straight down, and if you calculate the force work, you can use gravity, work against the gravity. Is mg initial position minus final position. If you calculate the work for this case, again, this is parabolic path. It's like a projectile, but it depends on initial position and final position, which is this height. So in other words, it is independent of the path, but depend on the initial position and final position. So basically this case and this case are identical because you will get same work. Okay, here's the second example for the second version of conservative force. If the force is conservative when it does not work on an object moving around a closed path. So if you start from this location and we have a height h, initial height, and it goes around like this and then come back to the final position. So h final and h naught are same. So this means this term is 0. So therefore W is 0. So the work is 0, which means the force we applied to take these cards along this path is conservative. If the force is conservative when it does no work on an object, which means the total work is 0. So in real situations or normal situations, we have both non-conservative forces and conservative forces contribute to the total work. For example, if an object moves along on a surface, horizontal surface, we know there's a friction. So friction is now is a non-conservative force. So therefore the total work is the work done by conservative forces plus work done by non-conservative forces. So the work is, we know work is kinetic energy final minus kinetic energy initial, and also we know conservative work is mg h naught minus mg h final. So if you substitute this equation, so the final result is non-conservative force is kinetic energy change, delta is for change, plus potential energy change. So conservative force work done by conservative forces is kinetic energy change, which is Ke final minus Ke initial, and potential energy change is potential energy final minus potential energy initial. So if you rearrange Kef plus Pef is the final energy, kinetic energy plus potential energy is final energy, and kinetic energy initial plus potential energy initial is initial energy. So conservative work done by conservative force is, we can write final energy minus initial energy. So if you assume there are no conservative forces, like no frictional forces, or we're going to do it for simplicity because with non-conservative force we have to consider friction, heat. So it's then our calculations become more complicated. Therefore we can assume there is no heat, no resistance, and we can make some assumption depending on the situation. And if this is 0, if you assume there are no non-conservative forces, then we have this side becomes 0, and therefore E final is equal to E initial. So the final energy of a system is equal to initial energy of the system. So this means the total mechanical energy of an object remains constant as the object moves, provided that the net work done by external non-conservative force is 0. If this is 0, E final is equal to E initial. So final is kinetic energy final plus potential energy final is equal to Ke initial plus potential energy initial. So this equation we call it principle of mechanical energy, principle of conservation of mechanical energy. The energy of a system is conserved. Final energy of a system is same as initial energy of the system. There is no energy loss due to heat or resistance or wind energy. So there are so many things it can change the final energy and the initial energy difference, but if we assume non-conservative forces are zero, E final is always equal to E initial, and this is called principle of conservation of mechanical energy. In the previous slide, we learned that total mechanical energy, total mechanical energy total mechanical, which is kinetic energy plus potential energy of an object is constant when the object moves. Okay, let me take an example. So let's say there's an object coming down the hill, and now it's at the bottom of the hill. So here we have a kinetic energy which is associated with the velocity or speed, and also you have a potential energy. Anywhere in the middle also has kinetic energy and potential energy, and also bottom of the hill it has a kinetic energy and potential energy. The total, the kinetic energy plus potential energy at any given point at the beginning or at the end or anywhere between beginning and end, this total kinetic plus potential is a constant. For example, if the, let's say at the beginning kinetic energy, let's say 0, and potential energy is 140. In the middle, kinetic energy can be 70, potential energy can be 70. So if you add these two, it's 140. If you add these two, the total energy is 140. So if you add this, let's say here it has kinetic energy 120 and potential energy is 20, still it's 140. So when the object moves, its kinetic energy can change, but potential, if kinetic energy increases, potential energy decreases. Because when something is keep moving, we know its velocity keep increases, because kinetic energy is half mass velocity square. So if something is keep moving, its velocity increases, which means its potential kinetic energy increases. How about the potential energy? Potential energy is half mgh. When something is coming down, the height decreases, which means the potential energy decreases, kinetic energy increases. So if the kinetic energy decreases, then potential energy increases. It happens opposite, so that the total remains same. So which means the mechanical energy, which is kinetic plus potential of an object, is a constant, which is this value. It's not going to change. Okay, here's another example. So this at the beginning or top, the velocity is 0, therefore its kinetic energy, half mass velocity square, is 0 because it's not moving, but its total potential, because mass, gravity, height, because this is the maximum height. And if it is start moving in a situation like this, it has a little bit of kinetic energy and potential. So if it is coming down, you see its kinetic energy increases and potential energy on the other hand decreases. The reason kinetic energy increases because it has the velocity. Velocity keep increase when it's coming down this track. But potential energy decreases because the height with respect to this position, if this h is 0 and this is the maximum height, so height decreases and velocity increases. So therefore kinetic energy increases, potential energy decreases, but the total remain constant if there is no non-conservative work, because we assume that there is no non-conservative work, there's no friction, there's no loss of heat, so if everything is constant, then there's no conservative forces, non-conservative forces. This is a good example for projectile motion. And the question is, ignoring the air resistance, the speed with the cycle strikes the ground on the other side. So what is the speed? So if in previous chapters we learn how to solve these equations using kinematic equations. Now we can use the conservation of mechanical energy, which is final energy, kinetic energy final plus potential energy final is equal to kinetic energy initial plus potential energy initial, to solve this problem, because here he has a speed. Therefore, we can write initial kinetic energy half mass of the cyclist and the velocity, which is 38 meters per second square, okay, plus potential energy is mass, gravity, and the height is 70. Okay, at the final is right here. So kinetic energy is half mass v final square plus how the potential energy, mass, gravity, and height, 35. So kinetic energy final, potential energy final. So only variable is V final. So mass is common to all four terms. So we can cancel mass on all four terms. And gravity is 9.8 meters per second. 9.8. And now you can solve V final. Now we learn another way to solve this kind of problems without using kinetic equations we learned in previous chapters, and here we use conservation of mechanical energy. Final energy is equal to initial energy, which is total kinetic plus potential. Okay, here's another example. At this location, we can write kinetic energy plus potential energy, and here also we can write kinetic energy plus potential energy. Kinetic is half mass v square plus potential energy is mgh. So half mass v is 0, so therefore 0 square, this term becomes 0. Mass, gravity, height is h naught. And here kinetic energy is half mv final square plus potential energy is mg H final. So if you know these values, so this final is equal to initial, and then you can calculate uh, any given value or any. So definition of average power. Power is rate of change of work. Work we learn how to calculate using a couple of different ways. One way is net force multiplied by displacement, or half mv final square minus half mv initial square. So work, and if you know the time, we can calculate the power, rate of change of work, and joules per second, because units of work is joules, unit of time is seconds, SI unit, and joules per second we use one word, we call it watt. Watt is unit of power.